real exam questions. This is question 1 about beams and compression reinforcement. The question is, when do we use compression reinforcement in the case of simple bending in ultimate limit state? And simple bending means that any D is 0. Then the second part of the question is why, and followed by prove the following formula for the calculation of the needed compression reinforcement. And what does the symbol limit mean? Third part of the question. One of the goals to use compression reinforcement is making sure that the steel is yielding in ultimate limit state. To obtain this, the reduced bending moment, the limit, must be smaller than 0.371, and this is required to avoid brittle failure. It means that the sag of a beam should serve as an early warning system for failure. So brittle failure we want to avoid. Second reason why we are using compression reinforcement is to reduce the concrete compression height. To obtain this, the reduced bending moment with the limit must be smaller than 0.296, and this is required to assure rotation capacity of the section and to acquire ductile behavior. For instance, beams in a continuous framework must have sufficient rotation capacity to redistribute the bending moment. So we are here, in fact, limiting the depth of the compression zone or the position of the neutral axis. We are limiting this to 0.45 times the effective depth. Now we have to prove the set formula, the formula for calculating the resistance, the bending moment resistance of a section with tension and compression reinforcement. Let's see at a section with AS1, the tension reinforcement, AS2, the compression reinforcement. The position of AS2, or the point of gravity, is D2, and the point of gravity for the reinforcement in tension is D1. The difference in distance, I call it L, and the total force coming from the compression reinforcement is Fs2. Now first, delta MD is the additional bending moment to be covered by AS2. So that's the additional bending moment that we will obtain to achieve some goal. And this goal, we call it target bending moment. So you want to reach something, and that's the target bending moment. So of course, the additional bending moment is then total bending moment minus the target bending moment. Or you can write it like this. But the target bending moment is equal to mu limit times BD squared FCD from the definition. And mu limit is the target that we want to obtain. So when we substitute MD limit, we arrive at the equation that the additional bending moment to be covered by the compression reinforcement equals the total bending moment minus the target bending moment. But the additional bending moment to be covered by the compression reinforcement is, of course, when we take the rotation equilibrium around the point of gravity of the tension reinforcement is, of course, equal to the Fs2 times L, the distance L. So the distance L is the effective depth D minus B2, and the force Fs2 is, of course, the total amount of total area of compression reinforcement times the stress in the compression reinforcement and times D minus D2. We do not know at this moment what is sigma S2. But we can we can now calculate the compression reinforcement, which is the additional bending moment to be covered by AS2 divided by this. Now we look at those two, we can substitute the delta MD into this formula, and we obtain the formula which is giving us the total amount of needed compression reinforcement to obtain the goal, which is mu limit. What does the symbol mu limit mean? Well, let's make a small drawing of the strain diagram. This is unloaded section. On this side, we have the strain of the concrete, the compression, and on the other side, the strain of the steel in tension. The target reduced bending moment, working in the area of simple bending, it means we are situated between those two load cases. And first of all, we take as example the rotation capacity. So this is this load case or this shape of stress of strain diagram, and to achieve additional or sufficient rotation capacity, the position of the neutral axis or the total height of the compressive zone must be smaller or equal to 0.45 times d. So that defines this line or this load case, and it corresponds with a reduced bending moment of 0.296. So that is the target reduced bending moment. Target is rotation capacity. The second example is ductility, because we want to obtain yielding of steel. This is here the stress in the steel, reinforcement steel. And then we see that the to achieve yielding of the steel, to achieve FAD, we are at this strain. Then we connect this strain to that point. So the red situation or the red load case is the load case where we achieve sufficient ductility of the situation, yielding of the steel. The compression of the depth of the neutral axis is then equal to 0.617 times d, and mu limit is 0.371. So the two targets are rotation capacity and the yielding of the steel.